Okay, so we got problem 7.17. It says the 165 volt and 5 ohm source in the circuit in this figure is invertly short circuited as its terminals A, B. At the time the fault occurs, the circuit has been in operation for a long time. Okay, so a time before 0, this circuit looks like this. The inductor turns into a wire for t greater than 0, and then I'm gonna right. And then we're gonna do another circuit for t greater than 0. Okay, so it says what is the initial value of the current IA, current IAB, the short circuit connection between terminals A and B. Okay, so I'm gonna do part A first. Yeah, so this 165, assuming this here is our ground. Call that V1. We call this I1, I2, I3. So we got KCL is I1 equals I2 plus I3. Equation for components. I1 equals 165 minus V1 over 5. I2 would be equal to V1 over 5. I3 equals V1 over 3. And then we got 4 equations, 4 variables. So let's go ahead and do that. Oops. 1 equals 2, 3. Minus V1 over 5. Okay. Okay, so these are our values. So now this is for time less than 0. Or yeah. Now we want to do for time greater than 0. So for time greater than 0, I'm just gonna redo this again. Okay. This is 5, 1, short circuit. Then we got 9 amps going through here. And then we got and we got 15 here. So I'm gonna call this IS, I1, 2, 3. These I2 and I3 isn't really necessary. Let me make sure. Yeah. So okay. So then yeah, there's no really need for KCL here. You can just go ahead and find IS. No, IS is equal to Ohm's law. B over R, 165 over 5. 33. So yeah, we know. So we got 33 equals I1 plus 9 plus 15. I1 is 9. So our terminals A, B. So the initial value for current across the terminals in the short circuited connection is 9 amps. Okay, so then for solving for B, so this is our answer to A. We got B. What is the final value of the current IAB? So there's no really need to analyze the circuit here. We know that there is going to be current here inside these inductors. But over a while, over time, this here is just gonna turn into the resistors and an inductor. So essentially, what our circuit would look like would be like this. And those 33 amps coming out of here are, so the final current IAB is going to be 33. It's going to be essentially, yeah. So current is going to follow the path of least resistance. The kinetic energy here inside is going to be depleted. And yeah, I think that answers the question. So it's going to be IAB equals I1 is going to be 33 amps. Okay. And so now how many microseconds after the short circuit has occurred is the current in the short equal to 19 amps? Okay. So now we got to work with the short circuit as well. So make a short circuit here, right? Amps. Well, there's things to know here is that, so for C, we know that I1 at 0 is going to be 9 amps, right? You know this from, oh wait, no, not I1, I2. For using this here, yeah, we're going to call, I guess we could call, you know, that the current coming out is 33 amps. I'm going to call this current IAB, call this I1, call this one I2. So yeah, and then I1 at 0 would be 9 amps. I2 at 0 would be here 15 amps, right? And for both at infinity, it'd be equal to 0. Okay. Okay. So how many microseconds after the short circuit has occurred is the current in the short circuit equal to 19? Okay, so we want to find the function of time for each current going through I1 and I2, each of these inductors. So we want to replicate this. Okay, so to replicate something along these lines, we need the tau. But we're able to find the tau. We have our equivalent and our L equivalent here for each in the wire. So you have 12 for 12.5 millihenry over 5, and then our tau for the 3.75 millihenry inductor. And we can do over 3. So if we plug these into a calculator, 12.5 and 3 over 5. This is going to be 0.0025, then 2.75 e to the 125. Okay. Okay, so then now that we have these values, I'm going to move this down here. That gets more space. There. 0.0025. So this 0.0025 1 over 400, so it's going to be 9 e to the negative 900 t. So same thing here. 0 plus 10 plus 0 t over 0.00125. 1 over 0.00125 is 800. Okay, so these are our values here. Okay, and we know that let me separate that, this, and then we know that current IAB across is going to be 19, right? or 9, I believe. No, yeah, it's yeah, no, no. It's so how many microseconds after the short circuit has occurred is the current short circuit equal to, yeah. So it's gonna, we have, it's given the value 19 amps. So then we formulate this, we do our KCL, so we know that 9e to the negative 900 t plus 15 e to the negative 800 t plus 19. And yeah, so this goes here. So 33 minus 19 is 14 equals 9 e to negative 900 t plus 15 e negative 800 t. So oh, what am I doing? It's not, it's 400. Negative 400. Okay, let me make sure that's right. Yeah, 400. That's right. 400. Okay, so once we get here, what do we do? So we look at our E. So we can convert this E. So if we were to square e to the negative 400t, we would get e to the negative 800t, right? So right. So we can call e to the negative 400t, call it x, and then e to the negative 800t, we'll call it x squared, right? So then I can go ahead and formulate a quadratic, right? And say 15x squared plus 9x minus 14. So then we can find our x, and our quadratic would look like this. So we get a positive and a negative value. The negative value is not applicable, so we go with the positive, right? So go, we know x is e to the negative 400t equal to 0.7116. And then off this, you can just let the calculator do the work. And oh, for this value, I got 8.506 e to the negative 4 seconds, or 8.506 times 10 to the negative 4 seconds. So this happens it takes very little time for the short circuit to equal to 19 amps. Yeah. And yeah, this is the answer for 7.17.